Okay. So, a very good evening to all respected members in the panel, and a very warm welcome to all the participants in this webinar.
Yes, it is visible.
Shall I? And you can hear me also properly?
Your voice is also clear, very clear.
Okay. So, so good evening, everybody.
Professor Durba,
Thanks again.
Professor Durba, can you hear me? Hello?
Yes.
Yes, actually,
Yes.
Let us start.
Let him continue. Dr. Chakraborty.
Okay.
Let him continue. Okay, thank you, Professor Durba. Welcome to this webinar. And continue your presentation.
Thank you. All right. So I'll go ahead and continue. So good evening, everyone. Thanks once again for the invitation to give this webinar. I'm very glad to be here. Glad to meet your respected Vice Chancellor and all other participants here. So I'm going to talk about AI and high-performance computing for extreme events detection monitoring using Earth observation. So before I talk about this AI and high-performance computing, let's talk a little bit about the Jio Computation, because whatever we are talking is more on the computational aspects. So the Jio Computation is all about applying computing technology to geographical problems. And these geographical problems in the recent years, probably a decade or so, has become even more prominent, because everybody is now worried about location. So if you open an app, it asks for a location. So it's trying to ask your location to give you more precise, more different insights into the way you're looking at a problem. So location is giving you a lot more than what you had earlier. So the geographic problems are now or more in mainstream, and then computing technology is now integrated with all of these things. So the computational theory of complex spatio-temporal processes, for example, is also a Jio Computation. So how do we use these new computational tools and methods, and how do we use it, especially to understand this process is all Jio Computation. So so before I go into the actual the problem with streaming data is that you cannot develop models, machine learning models that you are early used to doing, because the streaming data is constantly changing. So there is a drift in the concept of what it was, it showed an hour back and what it's now. So the model that you have developed based upon earlier data. So earlier data here could be just minutes to hours or even seconds. The model is no longer useful. So streaming data, and which is particularly if it is on a say mobile platform, for example, a sensor on a truck, and it's streaming information, data at you. If you want to build models, it's totally a very different way of doing it. So our normal machine learning models no longer seems to be working in that context. So the other is these days, everybody is contributing this geographic information. So a lot of it is called crowdsourced information or volunteer geographic information. An earthquake happened in Nepal. A lot of people were giving tweets. In a National Remote Sensing Center in Hyderabad, they had actually developed a crowdsourced application where people would download it on their mobiles and then provide information. And for example, Digital Globe, which is a remote sensing satellite imagery providing company, has put up a lot of high resolution data after disasters. They have put for many disasters. At the images, high resolution of destroyed roads near you, or destroyed buildings, or flooded bridges, all kind of event has happened. A flood has happened. What normally looks like in a normal image, the signatures are totally different. Spectral signatures would change. If in a quake, the shape would change, the structure would change. So it's not easy for us to do this. So it's important that we understand how do we take care of these things. This is another example of estimate intersection delays from floating cars data. So as I was telling, it is coming just like that we are providing, and then saying, okay, since you're going on this road, ahead there is a block, or ahead there is slight delay, expected delay on this road. To tell, because and a slightly different way of looking at these things. So I am now going into to discuss about how actually we can use this geospatial or Earth observation data. So Earth observation data could be from multiple ways you can acquire. You can acquire from satellite-based remote sensing, airborne, spaceborne, or ground-based sensors. Surface, subsurface, underwater, for example, under ocean. These are all Earth observation data sets. But today, mostly I will focus on data that is coming from satellite, from spaceborne sensors. So as you can look at in this slide, there is a lot of crisis data that is coming at because of so many different disasters. It could be earthquakes, volcanoes, or hurricanes, all kinds of things. So there is this term called big crisis data that is really coming up these days. So what does this mean? So it means that we are looking at a very large volume of data. So volume in the sense, a lot of satellite data that is being collected. For example, in Nepal earthquake that happened, data from about 18 sensors are collected at National Remote Sensing Center. So this was a nodal agency that was supposed to collect all this data and distribute it to all neighbors and all those centers who are doing this analysis. So the large volume of data, we need to fuse all this data, because and then the problems are this data could be in different resolutions, different spatial resolutions, temporal resolutions, spectral resolutions. So huge computational challenges involved. And then velocity, and all this data is coming very quickly at you. And then a variety of digital information, a lot of this, so much variety in this data that is coming because of this spatial, temporal, and spectral resolutions. The problem is, how do we take all this data and do that in near real time, so that we can give situational awareness to the people on the ground, actually, who are trying to respond to these disasters. So, because I said big data, and then big data is a buzzword these days. It is as if we weren't able to do anything with small data. earlier. People were also doing a lot of great things with small data earlier. So why big data? What is this big data? If we are looking at a large amount of data, what is it? Or you actually getting it? So one of the interesting things that you will get is that as the data becomes larger and larger, maybe quite possible, there's no guarantee, but there's quite possible that things that are looking linear in nature may slowly seem to turn out to be non-linear in nature. So those relationships between variables that we are actually trying to understand, which may be linear if we are looking at a very small amount of data, maybe the non-linearity will slowly emerge if we are looking at a very large amount of data. So this is a very important thing, so that our models accordingly we will try to develop. We'll try to now use a non-linear approaches to develop, to do some kind of non-linear modeling instead of a linear, which we thought is because we haven't had enough data to look at to understand it. So coming back to our disaster situation, so there could be different ways of disasters could happen. Floods, for example, Thailand, earthquake, Haiti, tsunami, Japan, right? So what could be the problem is if the flood has happened, as you can see, there is a change in the spectral signature. On the top, you have seen before disaster, and bottom is, these are from high resolution data sets. So this is a Thailand data sets of floods. So before and after, if you can see, there's a change in the spectral signature. And then the earthquake, you can see Haiti before and after, where there's a change in shape. And then you can see the tsunami that happened in Japan, and you can see what's happened. So all these, I'm sorry for all these captions on top. Actually, this is supposed to be run from a PowerPoint. Since we are having some issues with sharing the screen, I think this is more like a PDF kind of a thing. So we need to put up with this. So what we can see is, if in these two cases where there are floods and earthquakes, a lot of times the problem is we will not be able to get enough training samples. A lot of participants here are interested in developing machine learning kind of models. As we all know that in developing this kind of models, training data is very important. If we have a good amount of training data, we got good amount of pure samples that represent our classes. Yes, we may have a good training. We may have good models, but the problem in this kind of situation is that you don't have the luxury to collect a lot of training samples. The place is just too hazardous to go there and find out what it is. There's no ground truthing. Cannot happen. Even if you do this, you'll be only picking up a few samples, so you don't know the models that you have built, how accurate they are. You cannot do the validation properly. So to circumvent this problem, can we actually develop good models with small sample size? So the key word here is small sample size. But as we know, a lot of these models, machine learning models, require large number of samples. If you go into the deep learning domain, it actually requires much more training data than what other non-parametric approaches require. Although deep learning is proven to do much better now, but it requirement is huge. Training data sets are required, but we don't have the luxury to do it when disasters happen. So in the first two cases, it is like what we know before the disasters happen, how the image look like, what are the classes, what are their characteristics. Can we somehow use that knowledge and then transfer it when we are actually building models after the disaster? So post-disaster models are built based upon what we understand about situation before it. So this is called as a transfer learning. So transfer learning is is a slightly newer entry into this machine learning domain, probably not too, about probably a decade old. And then in both these situations, probably floods and earthquake, you have the luxury to do it. Probably in tsunami case, where you can see that after the tsunami has happened, totally new classes have come. So it is very difficult for us to actually transfer any knowledge what we know before. So I'm now going to talk about 4 challenges. The first challenge is when a disaster has happened, how do we do an automatic damage data identification? So what are we looking at? We're looking at buildings, built up areas. What happened to them? If there are, it's a flood disaster, we're looking at flooded areas, flooded vegetation, flooded urban areas, flooded roads, flooded buildings. Those are the kinds of classes. Quickly, we want to know, we want to map them and then make an assessment of the extent of the damage. And so to be able to do that, our challenge is, what is that? Search and retrieve relevant image content from multiple sensors data in near real time. So as I said earlier, there is this veracity, a lot of, in big data paradigm, velocity we have, then there's a veracity, then there is, volume. So here there are multiple sensors data and near real time. How do we take all of them to be able to do this? So one concept that normally happens when we are doing this kind of ways of analysis is what is called as the semantic gap. So if you see the picture on the left where an image was taken and then a segmentation is done on it, you can see the image regions in grayscale. So each image, normally if we are doing object-based classification, what we tend to do is we take each of this region and try to extract some features which are representative of, which tells us something about that region. So these features could be from a colors, texture, shape, all kinds of things. So what is that image is telling us? Image is actually telling us in terms of low-level features. It's saying, look, I'm a region. You can look at my texture. It's a coarse texture. You can see. I have some spectral information for you. And then I have some shape information for you. This is what the image is speaking to us. But the user who is looking at this image is at a much higher level. He doesn't care what the image is talking about. He is saying, okay, that's fine, but tell me, are you an agricultural land? Are you a wetland? Or are you a flooded area? Is that what I mean? So users thinking is much higher. It's a semantic, it's more higher conceptual level. So the problem is this gap between users thinking and what the image is trying to tell us is called what is called the semantic gap. So it is possible that we need to bridge these two things using what is called as knowledge representation. So you take these primitive features and then develop some kind of ontologies. Some of you may already know about it. Ontology is like capturing this shared understanding of a domain. So a lot of image-based ontology, image descriptions ontologies are now available. It's a big area. And then normally we use web ontology language to describe and the understanding of that domain. And then we can link these low-level features to the higher conceptual level. So once we take care of this semantic gap, we should be able to ask a lot of queries. For example, a semantic class called agriculture. If you see in this picture, we developed an application where user can search an image content for various classes. So, for example, a huge archived image of Landsat is there for 10 years of data, and then I want to search all agriculture areas in that image archive. See, normally if you sit and look at all of them, it's very difficult. Otherwise, there's no way to search imagery because you can only, search images based upon its syntactic metadata, what it is described, but not on the actual content. But if you are able to bridge the gap between the low-level primitive features and higher semantic, we should be able to do searching, link through ontologies. So So in this example, you can see how you can search in an archive for a semantic class, and then it brings up a lot of images that have got that class, and then further you can see that the regions that it has brought up what is actually, and you can also see what is the accuracy with posterior probability, which is telling that how much it is correct. So if take the same concept and apply it for disasters. So this is an archive of Katrina hurricane that happened in US probably a decade back. And then this is a Landsat imagery. So you can select an area and then select a sensor. You can either select the Landsat data sets or much high resolution data sets depending upon what archive data you have. And then you can select various semantic classes. In search here, you can see that flooded fastlands, all flooded urban related areas are there. It's able to quickly search and bring all this content. And then you can also see what is the confidence value of a particular retrieval of this thing. So these are all built based upon machine learning, but machine learning integrated with knowledge representation framework ontologies together. So if you ask me, what is the classification algorithm here? It's an SVM algorithm, the SVM classification, but then there is a linkage between the semantic concepts and others based with ontologies. So the challenge two. So challenge one is we want to search for images, but the problem is it is because there's not a whole lot of training data available because of the disasters. So unless I have this good training data, challenge one, I cannot make it in a good way because I can't have a good model. So if I don't have good models, I cannot search the archives with those models. So there's a problem. So challenge two is that since we need to somehow learn to work with very small samples, and then but still try to have a fairly good predictive classification models. So how do we do that? So if you look at the left side picture here, you can see that the traditional machine learning approaches, traditional classification. You can see that we can build different classes. I'm just interrupting. Am I audible to everybody? Hello?
Yes, you are audible.
Okay. I'll go ahead. Sure. So if you look at this left side picture, what we traditionally do is build different models for each class. So agriculture, I will create a model. Either I do a binary classification of agriculture versus the rest of the classes, or I will do a multi-class classification, multi-class model, and then build these different models with each other. This is what we do. Why we need to do this? Because to be able to build these models, there should be a training data. The algorithm should see the whole training data, the whole hypothesis space it needs to understand before it can form some understanding of it and then say, okay, this is what I understood and this is the model for this one. But what happens is a lot of times we may not have this kind of a training data involved. So it is possible that we can transfer what we know between classes if they are closely related. On the right side, if you see this hierarchy, a forest, agriculture, and swamps, if we just visualize in our mind how a forest looks like on an image, or an agriculture looks like on an image. So whenever I say image, I mean satellite image. So it could be a false color composite of a Landsat, for example, or it could be a true RGB image on whatever resolution we're talking about. So if you see these three classes, quite possible that that probably we can take some knowledge from this and learn a new class called flooded vegetation, or take swamps, marshlands, and lakes, and then take this knowledge and then probably learn a new class called waterlogged areas. Or if you take the other example, earthquake hit areas, urban areas, buildings, bridges, streets, can we take some information from this and learn a new class called urban areas destroyed? For example, by human conflict, someone bombed it, for example. It does look like an earthquake, but we may not be able to get good training data sets after that. But already we know how earthquake looks like. Already we know what buildings, bridges, streets look like. It's only they are in different form now, but there is some connection between them. So if you're talking about the ocean domain, harmful algal blooms, chlorophyll, chemical spills, how do we take this knowledge and learn a new class called oil spills? So new learning based upon transferring what we know prior knowledge between similar classes. So the keyword here is similar classes. If we try to, try to take knowledge and then try to, transfer between classes that are very different, very desperate in nature, probably it will not work. It actually counterproductive. It will be a negative transfer. So we'll have to understand and find out. So for example, water plus agriculture plus, I don't know what classes, if I combine together the knowledge, I should learn a new class called flooded agriculture class. That is where the experimentation, that is where the research is about. How do we take these things? So, so this is a Nepal pre-earthquake imagery. And then this is a post-earthquake, and this is quick bird images, very high resolution. So we did this work on taking this information from a pre-earthquake imagery and then post-earthquake, and try to use some information from this one and then see how do we actually create how do you build models. So if we just use an SVM model without any adapting, means transferring of knowledge. So this transfer learning is also called domain adaptation. So we can, as you can see in this picture, very poor accuracies. Here you can see. So this F1 index is based upon your precision and recall. But if we have used this, our approach of trying to transfer this, you can see that a very small sample size is the x-axis. If you see 2 samples, 4 samples, even as small as 2 samples if you have of the actual ground truth, still if we transfer it, because we are doing a transfer from pre-disaster image, we are able to get actually 60% accuracy, just like that. So the idea is that can we quickly, rapidly give some kind of an idea about what is the extent of this disaster by just taking few samples, do the transfer, do the domain adaptation, transfer this between pre and post disasters data images, and develop these models. So the same principle applied to the flood case, a pre-flood imagery and a post-flood imagery. This is a Srinagar images with pre and post-flood. As you can see, ordinary SVM is not able to perform well, whereas the domain adaptation is able to perform. But we must understand one thing here, that this kind of transfer is not going to give us very high classification accuracies, 90%, 95%. We will not, it's very difficult to get that much amount of accuracy, but at the cost of small samples. So a lot of times what we require is a fairly accurate kind of a model, sufficiently accurate, 70%, 80% accurate, but that which we can develop with very small sample size. Quickly we should be able to do it. So for disaster kind of situations, if we want to understand the very first cut of what happened on the ground, these are the kind of models, this kind of transfer will work well. So now we'll move slightly more into understanding more about the contextual information that an image is telling. So for example, look at a motivating scenario like retrieve flooded urban areas in a geographical area X, some area X, from imagery from a sensor Y, For example, this could be a quick bird imagery. So what is the current status and information about nearest evacuation areas, time to reach, what has been done in the past for similar types of situations, how are the local people responding, etc. So these are some guy control room wants to know whenever disasters happen. How can I quickly, now I'm getting all the satellite imagery, how can I now integrate all this together? What is happening? So the challenge 3 is, so challenge 2 may only enable to identify the affected areas. Fine, we use this small training samples. Now we are able to identify that this is a flooded road, that is a flooded building, or this is a destroyed building in an earthquake. All these things, fine, but does not give any information about the neighborhood or contextual knowledge. So we want to understand not only the affected areas, but the spatial context of the neighborhood area. So someone is asking me, good, you have told this building is flooded, but is there a road on the north of this that is still not flooded, so that we can use it somewhere to send supplies or whatever? What is happening in the neighborhood? What is the spatial context of other objects in the image that we want to know? So for example, retrieve all the images from an archive of satellite X, which have buildings surrounded by flooded area. We're talking about building, and also provide the details of nearby hospitals and nearby fire stations. So if we had actually captured hospitals and fire stations in an image, now we want to understand the context of these buildings. So when this building surrounded by water, and how it is placed with respect to the other things that we require now. So image information mining is an area that's been around a decade now, where a lot of this earlier work that I showed all belongs to the IIM area, where you can search content-based search, the semantics, knowledge representation, all come together. So on the right side, you can see a picture like this. On the picture, you can see that there's flooded areas, but people staying there inside a flooded area want to contextually understand how am I situated with respect to other things around me. Can I search those kinds of things on an images is what we want to actually do. So we developed what's called as a spatial image information mining. How do we take images and then search for content that have got some spatial? So for example, I can use spatial predict like surrounded by two objects touching each other like that. So in this framework, we also introduced a new way of storing content from image. For example, right now image content normally you store as a raster form of information, as a pixel information. How do we actually take the regions of an image and then extract the features and store them in a slightly different form, or not in the normal traditional databases? So the concept of RDF, resource framework and all has been brought in, although this is probably out of scope for this talk. But what I'm trying to say is, there is a different way of storing information that is extracted from image, so that later you can use it to do a slightly more advanced kind of searching than what normally you can accomplish. At the bottom, you see this storage, and then image ingestion, segmentation, different kind of feature extraction. So our proposal was to develop what is called as this spatial semantic graph. So this is a huge graph which links all the regions in the image together and between images, so that each region, how it's linked with another image, is all captured in this kind of a spatial semantic graph. So later we will use a reasoner to be able to search this graph and some rule engines to be able to do it. So at the top is our user interface. So what kind of topological relations have we encoded? We encoded, for example, tangential, proper part, non-tangential. These are called regional connection calculus. So in GIS, normally we are interested in understanding what are the different topological relationships that are happening between different objects. So one example is you open an app and then you are going and then you say, okay, I feel hungry. Is there any food court that is on the right side of this road in another 5 kilometers? So it means if that app is able to answer a question like this, it means it is able to understand this topological relations. It has somewhere encoded the relationship between the road that you have and a polygon that is on the right side of it, and that polygon, which is the food court. So there is a relationship between them. So these kind of topological relations that are there on the images, although these are possible in GIS, but not on the images, it's not very straightforward. So, and then in addition to these topological relationships, we also wanted to capture what is the directional relationships. As I said earlier, is there a road that is on the northeast of this flooded building or southwest of this thing? What are all the objects and what are the directions? Not only whether they are surrounded by or touching or overlapping, but we also wanted to know what is the direction in which this is happening. So these kind of directional relationships were also captured and then used. So for example, if you look at an image like this, retrieve all images from a repository where you can see which have flooded water. So, so on the left, you see the actual image that we are talking about. Can you see that? So this is the kind of data that we want to capture, and then we want to search it. So this is not too hard because this is only capturing, searching for a single semantic class from an image. So you can search for this kind of a pattern on image and get all the patterns from this one. Or you can also look at another query. So what happened here is, sorry, you are not able to see the queries because they're hidden behind because of this PowerPoint problem, but I'm going to read it. Show all images from a repository having built up regions adjacent to a river. So this is a query on the bottom, on the left side bottom, you can see all the built up areas that are adjacent to river. So in fact, what we are doing, built up externally connected to a river, is what this query is what going to do, and we will search that and then retrieve these answers. So look at another kind of a query. This is slightly more involved. It's asking about retrieve all images. So I'm sorry you're not able to read the full query, but I'm going to read it for you because I have it on my other screen. What this query is, it's both topological and directional. So topological means objects that are related with each other spatially, and directional is northeast, southwest, or north, those kinds of this thing. So on the left side, you can see a schematic, a picture that was hand drawn. You can see a river. So retrieve all images from a sensor which contains built up regions, rivers, and stagnated floodwater, such that we are saying built up or adjacent to the river. In the image, if you can see this on the left side image, built up or adjacent to the river and oriented strongly to the west of the stagnated floodwater. So here, what that we want a particular configuration to be searched on an archive with data. Why we want to do this? Because there's a huge archive, lot of data, lot of sensors are giving the information. You cannot sit there and glean all this information. For example, after Nepal earthquake happened, it took many days for people who are doing this analysis of the data to actually tell what is the extent of this disaster, because there are analysts sitting there looking at these pictures and using some kind of semi-automated methods. And so a lot of visual interpretation happens. We want to take away all these things. Can you just feed the image and ask for it and say can you capture this configuration and just give me all the images for based on this configuration. So on the right side, you can see this results from this one. And then the query 6, again, you will not be able to see the question, but I'm going to read it for you. Show all images captured by sensor, by satellite sensor, in which the industrial commercial regions stagnant water. And then we're also saying industrial commercial regions are weak north of stagnated flood water, and then weak east, so like the strong east, weak east information. So this is the kind of picture that you can see on the right side, the actual photographs. This is the kind of configuration that we would like to search on satellite image. So you can see that that it's very important to understand the context of what just detect the affected information, the relationship between objects, and then be able to query on them. So challenge 4. So this the challenge 4 is like, even if we address challenge 1 to 3, fine, we know how to search an image archive for a particular content. We know how to build models using small samples. We know how to understand the context. But even if we do all these things, if you don't do all this in a very small amount of time, it is still useless, because if you provide any information about after 24, 48 or 72 hours of a disaster, it's almost useless. You know, the information has expired. Nobody cares about that information. So challenge 4 is, yeah, do all these 3 things, but do it very rapidly. So rapid processing of post-disaster data from multiple sources is important. So various HPC techniques, some of you may already know all these things. There are cluster architectures, distributed computing, FPGAs. I mean, people not much use these days, but yes, FPGAs. So big data analytics, you can use this cluster architectures, and then these days, very popular is the graphics processing units, GPUs. This is what we do. We have got a GPU-based cluster here at CSRE. So we did some work on it. So a kind of a framework of using this HPC technologies. So if you want to do disaster analysis in real time, you can take different satellite data sets, real-time satellite data pre-processing, data analysis, real-time visualization, scientific visualization, disaster notification, plan of action, and then all these things. And then we want to do all this on a high-performance computing setup. So before even we do that, we need to understand where is the problem, where is that actually should we use HPC. So in this, our scheme of things of developing these classification models and all, you must have observed that feature extraction forms a very important part. But feature extraction is a very time-consuming operation if you're doing on regions of an image. So we wanted to look at and see how can we take this features extraction and then how do we parallelize it. So on the right side, if you see, and then once you can also, before feature extraction, normally we do something called as a segmentation. So on the right side, if you see a mean shift segmentation on a CPU, it is taking a lot of time. As image size is increasing, the time to do the segmentation keeps on increasing. And during disasters and all, we're not talking about 1 or 2 images, we're talking about hundreds of images. And sometimes because the spatial temporal nature, for example, flood, is that we are actually tracking for many days. Right? So there are a lot of images coming from multiple sensors. So even if you are doing for each image, if it's taking a lot of time, so quickly it becomes a very slow process. So texture feature extraction on an image size like this. For example, if you do the GLCM textured features, as the number of regions in the image increases, it becomes larger and larger. So heterogeneous computing, CPU plus GPU is the way to go. So where the computational highly intensive processes are delegated to a GPU device, GPU does that single computation for you, but it does that single computation on many processors parallelly, so that it reduces time and then gives back to the CPU to do whatever it is doing earlier. So CPU delegates to the GPU whatever the computation problem. So how do we go about doing this? So we need to analyze an algorithm and see where are the places where it is possible to parallelize. Not every algorithm is parallelizable. There are inherent sequential algorithms. It can't do anything much with it, but it is possible that a lot of this thing. So we need to understand at which places on an image, what kind of approaches in images we can do parallel processing. For example, if I'm doing neighborhood analysis, I am moving a window to do filtering. Yeah, I can do I can parallelize it. I can do a GPU processing. I'm doing a ratio-based operation between two images. No, it doesn't work much. It doesn't help me even if I do a GPU-based, a parallel-based computing approaches. So it is for us to understand where we should use a parallel processing, where we should not. So it is important in a framework that we have developed to solve a particular problem. We need to see which portions of this can be solved by parallel processing. Where can we speed up? This need to be understood properly before we use this in a GPU-based or HPC-based approaches. So we have conducted several experiments on images like this. For example, a mean shift segmentation algorithm, if you see this one, GPU time versus CPU time, you can see the blue curve is the GPU. As you can see that it's performing really well as the image size is increasing, whereas the CPU is slowly increasing as the image size is increasing. So we also conducted several experiments on different kinds of GPUs. And then normal CPU. So we used about 1600 tiles, 256 by 256, and then used the CPU, a mean shift just on the CPU part. You can see that it took about 3 hours to do this. And then this applied on a GTS 450. So G4 GTS 450 is normally there in our laptops, on our desktop computers. So anybody who wants to get started in the GPU parallel, they can just use it. They can start developing this nice CUDA framework, use the nice CUDA framework to do this processing. And then we also did this on a Tesla C2075 GPU. And then on a very high-end GPU cluster that we have, the Tesla K40 devices, as you can see, from 3 hours, now it became 24 seconds. So one component of our framework of building this nice disaster models is feature extraction. We have reduced it considerably to about 24 seconds. Now what will happen is, tomorrow if we are applying our framework, we already reduced a lot of the computer-intensive tasks by using HPC in it. So this kind of approach was also applied in oil spills detection. So oil spills are a huge problem these days. So this is from the Gulf of Mexico oil spill data that we have from Landsat. One of my PhD students has done this work on developing this framework and then using morphological profile, attribute profile features, and then use all that in a GPU framework. So we compared as the image size is increasing on an oil spill index, how it is performing. You can see the red curve. GPU is performing really well, even as the image size has increased, whereas the CPU is taking a lot of time. So GPU speed up is about 220 times faster for a particular kind of an operation within this thing, for a structuring element. So when you're doing this morphological operator, we use a structuring element. So as the structuring element size increases, so just think about it like a moving window, for example. As this is increasing, GPU is still performing okay. Whereas you can see that this one, this CPU is doing having a lot of problems in catching up. So this is another example of now, because deep learning is popular these days. Someone said, do deep learning or die. So everybody has to do deep learning. Just if you are applying and the train, it will take hours to do training. And what will happen is you set your training data, you set your hyperparameters and ask it to train. And after 5-6 hours, it will come back and give a poor result. Then again, you set it and do all these things again. So what is happening is there is no quick feedback on what we are trying to, when we are trying to develop this one. So training is a huge problem in this thing. So important thing is we take or do all this training on high performance computing so that the feedback is very fast. So you can quickly train more models in less amount of time. So here you can see that on a CPU, whereas GPU, you can see, although here you're seeing only in seconds, this is probably for a small data set, but still it is significant. So I'll end my talk with the last slide that shows about flood data classification using deep learning. So this is a multi-class results from urban flood satellite image. You can see the satellite image on the left, which is a flooded image. And how we have done this object-based classification using deep learning. And then actually performed all this on a Kepler 80 GPU from NVIDIA. It took about 57 minutes only, whereas it took about 953 minutes on a CPU. So thank you very much. I'll be happy to take your questions.
Thank you very much, Professor Durva, for this very informative lecture. He has talked about big crisis data, which arises, which we obtain due to various different kinds of natural calamities like earthquakes, tsunami, landslides, and so on. He has also discussed about the complexities when the data gets large, the nonlinear relationships between them. And he has also discussed about the changes in spectral signatures when these calamities take place, before and after the calamity, the changes in spectral signatures, the changes in shapes, the formation of new classes. He has also discussed about the challenges faced in collecting training data during these natural disasters, how transfer learning can help to fill up the data gaps. He has also elaborately discussed about retrieving images from a repository of images based on queries. And he has also talked about when to use parallel processing and when not to use parallel processing. Thank you very much, Professor Durva. I was not able to give an introduction of Professor Durva, so I would like to do so after his lecture. He is Professor Surya Durva, professor in the Center of Studies in Resources Engineering, CSRE, Indian Institute of Technology, Mumbai. He did his PhD in computer engineering from Mississippi State University, USA. He was the assistant research professor from 2009 to 2011 in the Center for Advanced Vehicular Systems, Mississippi State University. He was also an adjunct assistant research professor from 2007 to 2011 in the Department of Electrical and Computer Engineering, Mississippi State University. He was a scientist in the Photogrammetry and Remote Sensing Division, Indian Institute of Remote Sensing, Department of Space, Government of India. So presently, he is a professor in the CSRE Center of Studies in Resources Engineering, IIT Mumbai. His key research interests are in geospatial standards and semantics, knowledge-based systems, image information mining, Internet of Things, cloud computing, based geocomputations, interoperability, sensor webs, critical infrastructure protection, remote sensing, and biophysical variables retrieval from remote sensing data. So we have heard a very interesting talk from Professor Durga, and we have some questions also from the audience. And we also have Professor Jun Lee, who has joined us. So Professor Durga, will you stay with us?
Yes.
Will you stay with us? Can we take the questions after the second session?
Yes, sure.
Thank you. Thank you. So we also have our Honorable Vice Chancellor with us, Professor Dr. Shoykot Moitro with us. Sir, can you please make yourself visible?
Yes, hello.
Yes, sir.
Can you hear me?
Yes, we can hear you. So can you please, so we were not able to start the inaugural session. So in between, sir, can you please say something for the audience and for the speakers? After that, we can continue.
Professor Dhruva, and I am very proud to note that our geoinformatics department, they are organizing serially a number of these value-added programs for the benefit of our participants, particularly those who are pursuing academic career and research in the field of geoinformatics. This is one of our now prominent area, and particularly for this is the only university at the state of West Bengal which is having these types of programs, academic programs with the government collaboratively, and would like to introduce more programs in this under the banner of this geoinformatics in different verticals. And I wish that in near future also we will be having the support and advices from all these erudite personalities like Professor Dhruva and all others who are Professor Antonio, he presented previous stage, Professor Gopalan presented previous stage. So these are nice experiences, and I am seeing overwhelming responses. I would like to share this information with all of you because this panelists that here this webinar created a lot of this enthusiasms and interest among our students, our research community, and it is getting a lot of coverage in media also. And I believe that with all these things in near future, we'll be able to design and develop more emerging technology-based programs in the field of geoinformatics. So thank you, Professor Chakraborty. You kindly continue with your the deliberations, because we have another important speaker there. So people will be are eagerly waiting to listen to her. After that, we can have this lively discussions. And as you did last time, I have seen that you have created discussion forum. So the students and the participants and all others, they can post their query, and that can be a really a good example for building up further knowledge in this area. Thank you.
Yes. Thank you very much, sir. Yes, this is to kindly tell all the participants that we have a discussion forum. So besides answering the questions here in this platform, you can also carry forward the discussion in the forum. The URL of the forum is being given in the chat box. It is makout.geo.blogspot.com. So the participants can place their query, and I request our experts to please respond to their queries. Okay, so to move on with the next speaker, we have Professor Jun Lee with us. She has joined us. Professor Jun Lee, are you there? Are you able to hear us, Professor Jun Lee? Can you hear us? I think your microphone is muted. Can you switch on your video, please? Hello, can you
hear me?
Yes, yes. Very happy to see you.
Sorry that. Okay, okay. Thank you very much for your invitation.
Yes, I hope everything is fine. You were able, lots of pressure on you today. Flight coming.
Yeah.
Yes.
Yeah.
Thank you very much. Thank you very much for joining. Okay, so before we begin with the session,
I can.
Yes.
Things I'm okay, but I think it seems like.
Yes. Can you hear me? Can you hear me? Am I audible to you?
I cannot. I don't know what happened with my connection, but I cannot hear you well.
Now? Am I audible now?
I cannot hear you.
I see. Okay.
Can you hear me, Professor Lee?
Okay, so can you start with the presentation? I would just, you can start with your presentation. I would just give an introduction.
I'm going to cut.
Okay.
I think Dr. Chakraborty, you kindly text her, send a message requesting her to start the presentation.
Yes, yes.
Okay. It's like I'm going to cut my video then to have better connection, okay?
Okay, okay.
Yeah, yeah.
Now I'm going to share. No. Wait. I'm going to share my screen. Hello? Can you hear me and can you see the screen?
Yes, yes.
So I'm going to start, okay?
Yes.
Thank you very much for your invitation. It seems like my connection is not so good, so maybe during my talk it will be off and on. And sorry for this annoying issue, but I will try to make the talk, okay? My talk is Spectral Spatial Hyperspectral Image Classification. My name is Jun Lee, and I'm from the Sun Yat-sen University, China. And this is my website if you for people who would like to have some information for the talk. And I'm currently the editor-in-chief elect of the Actual Journal of Selected Topics and the Remote Sensing. Now, before I give the talk about spatial hyperspectral classification, I'm going to give some concept about the hyperspectral classification. Already, in this topic, I think in this seminar, we already have some idea. We already have some speaker. The previous one also talk about hyperspectral data. So hyperspectral data, it is a 3D data cube with a 1D represented the spectral domain and a 2D represented the spatial domain. Each pixel is a continuous spectral signature representing a class. From here we can see, okay, I'll give a brief introduction about the concept of hyperspectral classification. When we do hyperspectral classification, normally we have three kinds of information or three domains. We're trying to use the representations from three domains. The first one is the spectral domain, or we call it spectral representation. For example, here we have the three signatures. The blue represented the water, the green one represented the vegetation, and the other one is the soil. From here, we can see that each material or each signature are unique to represent the class we would like to identify or detect. Of course, the spectral information or the spectral representation strongly depend on the physical composition of the observed objects and also on the spectral resolution. For example, here we can see it is a Landsat spectral signature, and here is this hyperspectral spectral signature. From here we can see if by multispectral, of course, we more or less can detect the material, but it has a lot of confusion. It has some confusion that maybe the same material share different, they're having different spectral signature, and different material, they may share the same signature. The confusion in the multispectral much higher than the hyperspectral. In hyperspectral, we call or we say that we have unique spectral signatures. Okay, so the other domain we normally use to perform classification, it is the image representation. Here it is a hyperspectral image. We can see some spatial coordinates or spectral correlations from this image we can see. If we have random sampling and put it in the same spectral like size, we can see it is like completely with random sampling, we can see complete noise, right? So from here we can tell in the spatial domain or in the image domain, we have strong spatial correlations. And this is of course depend on the geographic orientation and the data analysis at spatial levels. This is no matter related with the natural objects, for example, forest or grassland or oceans, or man-made objects, for example, buildings, road in a line, in a line structure, and all of them, as we call it, is for Earth observation. Of the Earth observations, they always have the spatial correlations. So this information or the image representation is also very important. This strongly depends on the spatial resolution. If we have high spatial resolution, we have more textures, more details, and if we have lower spatial resolution, of course, it is expected to have higher homogeneity. Okay, so the final one is recently is a very active research area is the feature domain or feature representation. The feature representation, of course, it is strongly dependent on both the spectral domain or the image domain. It comes from either spectral domain or the domain. It is, we use some pattern recognition or machine learning approaches, or for example, subspatial representation approaches. Even now, one of the most powerful tools is deep learning. Deep learning is trying to find a better or deeper feature representation, to discriminate or to identify our objects or classes. So normally when we perform classification, we go through these 3 domains, representations to perform our classification. So when we do a classification, I think already some of the experts already explained, right? When we do a classification, the purpose of classification is to give a set of observations. Each of them are pixel vectors. The goal of classification is to assign a unique label, for example, building, road, grass, to each pixel vector so that it is uniquely represented by a given class. It's like this. Each one we give a class label. This is the task. We have an observed vector, pixel vector, and we want to have a class. And we just say if we just do spectral classification, it is like have the assumption that we don't have spatial correlation. All the pixels are independent to each other. They are independent to each other is the basic assumption, right? It's a global assumption. So we can have, when we do classification, we have a lot of paper, the sort noise, as we can see here, have a lot of noise. It comes from the independent assumption of the pixel vectors. As we mentioned or discussed that the Earth observations, they have spatial homogeneities, or they have spatial correlations. And from here, that means some of the regions or areas we should have homogeneity. In this area, they should share the same class. So it is important to have the spatial information. The spatial information can come from the image domain or the feature domain. Of course, the spectral information also can come from the spectral domain or the image domain, right? Now we have a better classification map with a homogeneity. And it is much better represent the real world. This is why we want to have spectral and spatial information to jointly perform for classification. That's what we say here. It is important to jointly consider the spectral and the spatial information contained in the remote sensing data to have a joint classification. So today in the talk, here is a paper. It published in 2019. It is a review paper and published in Transaction of Geoscience on Geoscience and the remote sensing. And if some of you are interested, you can download the code here in GitHub. Okay, and today the outline, it have several parts. One part is the spatial dependency system, and we talk about the paradigms of spatial classification and some typical method and experimental results. First of all, we are going to talk a little bit about the concept of spatial dependency systems. We want to drop off the independence of the pixel vectors. We want to introduce spatial dependencies. In the beginning, we first needed to introduce assumption that the pixels spatially dependent to each other. What is a spatial dependency system? The definition here it is, we call this an aggregate of pixel or label entities carrying spatial information and the connected neighborhood that has property of coverage and importance. In the next page, I will introduce it in more detail. Here we have two important parts with 4 terms. The first one, it is the pixel dependency or neighbor dependency. And the other one is the neighborhood. We have 2 factors. One is neighborhood coverage and the other one is neighborhood importance. Okay, for this figure, I'm going to introduce it in more detail. So, what is the pixel dependence? Pixel dependence, that means the pixels, they are have the same pixel, have the same vectors. From here, we can see that all the pixels, if they are spatially dependent, they share very similar spectral vector. We call this a pixel dependence. And what is a label dependence? A label dependency is that if they are spatially dependent, that means they have the same label. From here, we can see that in this region, all the this inside this neighborhood, they have the same labels, their class 1, right? So either the pixel dependency or the label dependency is defined, or the spatial dependency is defined by the neighborhood. By neighborhood, because the dependency only can work inside the neighborhood system. In the neighborhood, there are 2 factors. One is the covering. From here, we can see here it is not a regular or symmetric neighborhood system. We can see here we have 1, 2, 3, 4, 5, 6 neighborhood samples, pixels in the neighborhood, right? And this is one, the coverage of this neighborhood. And the other one, the other factor is the importance, or we can call it the weight. The weight, for example, here we can see that the up, bottom, and the left, right, these 4 pixels have the same weight with W1. And these 2 pixels, they have the same weight of W2. So from here, we can see that no matter they are, depending on the pixel dependency or depending on why the label, the label systems, they have are controlled by the neighborhood. They have maybe in this neighborhood, in this size neighborhood coverage, and then with this weight. The weight can be the same, of course, they can be different. The coverage can be with a regular size or with a different shape, with a regular shape or with a different shape. Okay, now we have the definition of the dependent system. Okay, so we have the definition and we have the factors. And then when we are doing, or in the literature, we have different systems. One is a fixed dependent system. What is a fixed dependent system? The fixed dependency system is that the neighborhood factors are fixed. That means the shape of the neighborhood is fixed, and the importance, the weights are fixed. We call this a fixed neighborhood system. For example, if we want to have a 3 times 3 no pass filter, right? If we want to have a Gabor filter, wavelet filter, it is a fixed dependent system, right? And it can move from the pixel, from the window, a fixed window, and with a fixed weight. This is a fixed dependent system. Sometimes we have an adaptive dependent system. The adaptive, normally the weights are changing according to the neighborhood, changing from one place to another place. And the shape of this coverage, the coverage shape are also changing from one place to another place. We call it is adaptive according to the scenario or according to the image. It is adaptive. And the other one, the final one is a global dependent system. What is a global system? The global system, that means each pixel or each of the pixel, no matter it is from the vector aspect or from the label aspect, are connected to any other pixel in the image. So all of them are connected. They're globally connected. It's a global dependent system. We are also going to introduce a little bit later in the presentation, okay, what is a global dependent system. And in the when we are doing this, when we are introducing this spatial dependent system in the literature or in the papers, we can see in the literature sometimes the work use a single dependent system, just use the fixed, or use adaptive, or use a global. Sometimes we use by layer dependent system. We use fixed and plus adaptive, or fixed plus global according to the problem we are attacking with, and use multiple dependent system. The other one is the multiple one. I don't know what happened. Sorry. Okay. The other one is the multiple one. Sometimes we also possible to use a multiple dependency system. Okay. Now I'm going to introduce each of these each of these categories. The first one is the fixed dependent system. For example, as I just mentioned, the predetermined determined maskers or filters. It's like we have a low pass filter, or we have a morphological profile or structure elements. It is like a preset structure elements. These are normally we do as a pre-processing style. It depends on the pixel dependency. And another one, for the label dependency, we have microfluent field. This is easy to understand. Sometimes we have the first order microfluent field, or the second order microfluent field. We perform post-processing to introduce spatial homogeneity. It's a microfluent field. No matter the first order or the second order, both of them are fixed dependent systems. For the adaptive dependent system, for example, some of the work use age-sensitive factors. The neighborhoods are adaptive to the age, the age from one region to another region, from one area to another area. This normally are integrated with the pixel dependency. And for and another style, it is a superpixel. Superpixel is a very powerful and very used a lot in the literature. Used a lot solution or way to introduce the spatial dependencies. Is one of the most powerful way to introduce. It is also through the pixel dependency way. And then there's some other methodologies, for example, object segmentation. All of these have a similar style like superpixel. For example, the recognition software is like a segmentation style or object style. And another one for the adaptive dependent system, belong to the adaptive dependent system category. It belongs also to the label dependencies, the voting. For example, the majority voting in the box or in the considered area, and we use a voting style to define the class of the segment. It is a voting style. Okay. Finally, for the global dependent system, one of the most formal, most powerful, or most common way solution is the conditional random field or maximum a posterior margin. These are the two methods. Now we summarize this. You consider global dependent system, that every pixel in the image are connected to any other pixel in the image. This is quite difficult, but it's very powerful. Okay, now we already introduced the concept of the. We already introduced the concept of the spatial dependent system. So the spatial information are introduced through this dependency system, rather than the spatial information is already introduced, and it is so that the spatial the pixels are correlated or in through the neighborhood system. Now we are going to introduce how to introduce or to integrate the spatial and the spectral information. We call it spectral spatial classification. We call it spectral spatial classification. That means we have an integration stage or a fusion stage. In that stage, that the spectral and the spatial information are fused or integrated. We can classify or categorize the methods in the literature to three kinds or three categories. The first one is the pre-processing style, or we call it a pre-processing based classification. In the pre-processing based classification, the spectral spatial information are are extracted, or they are integrated, fused prior to the feature-wise classification. Normally we use feature extraction to extract the spectral spatial information together, then perform a feature-wise classification. It's a pre-processing style. Then another one is the integrated style. In the integrated style, now that the spectral spatial information, they're integrated. They're integrated as input to the classifier. Then during the classification, we have the classification and the fusion together. Okay, and the final one is the post-processing style. In the post-processing style, normally we first perform the pixel-wise classification. And we have the pixel-wise classification. In this pixel-wise classification, we have the assumption that the pixels are independent to each other. Then we have a spatial regularization to fuse the spatial information and the pixel-wise classification result. Okay, through this style, or the pre-processing style, the feature extraction, and in the integrated, we have the fused classifier, or the post-processing in the spatial regularization. In such ways, we can fuse or integrate the spectral information and to have a final spatial classification output. Okay, so now we are going to summarize the pre-processing based classifiers, the properties or the characteristics. In the pre-processing based classification, the most important advantage is that we have new features. When we do, because it's a feature extraction strategy, okay? It's a feature strategy style. In the feature strategy, can you hear me? In the feature extraction strategy, we obtain new features. The new features can bring or reduce the uncertainty of the data. And of course, the likelihood function of a parametric model becomes sharper, and the increase then in this way that we are going to increase the average convergence of the class condition data, and the overlaps of the various class condition data distributed tends to reduce. So that means what? That means with the new feature, we have less error bound, we improve the error bound, that we improve the separability of the classes. We improve the separability of the classes. That's why we can introduce a much better classification performance if compared with the original data. This is the main reason that, and the main advantage is that we have new features, okay? Now, a simple way, for example, we have a hyperspectral data, we perform the extended morphological attribute profile, we get new features. Compared with this new feature, we have better class separability. We simply use a SVM classifier, we can get very beautiful classification result. I think this is one of the most powerful tools now we have, network, and we introduce, okay? In the integrated classification, the purpose of integrated classification, of course, it is to have better optimization of the classifier, okay? To reach the error bound of the original data, to have a better optimization to reach the error bound of the data. So the optimization range and the feasible region that are determined by the objective function and the constraints become more valid and restricted. That means compared with simple spectral classification, we can more quick and more easier to reach the error bound, okay, to reach the upper bound. We have, for example, one of the examples, we have the original data, we consider the spatial information, and we consider the spectral information. We integrated them then to a CRF conditional random field, and then we have the final classification result. Okay, and then we have the post-processing based classification. In the post-processing based classification, it is then eventually it should arrive at the same solution what in the integrated classification is supposed to obtain. because the features or the data is the same. So the purpose of the post-processing based classification is also to obtain it is also to obtain the upper bound of the data. The impact or the effect of the post-processing based classification is just a post-localization. It aims at shaping the pixel-wise a posterior distribution. The purpose is to arrive at the upper bound more quickly. The same purpose like the integrated classification. This is an example. For example, we have a hyperspectral data. We have a probability classifier. We use an MRF-based regularization then to sharpen the pixel-wise result. Then we have a classification map, of course. It introduces the spatial homogeneity. Okay, so now we are going to introduce some typical method. The first kind of method, or one of the most powerful methods, is we are going to introduce pre-processing or feature extraction. We have a fixed window, right? A low-pass filter window, and some, for example, local harmonic analysis. For example, we have a gap filter. We have a varied filter or other kind of local harmonic analysis, right? And also we can have even adaptive structure elements to perform the structure filtering. Structure filtering is one of the most powerful way or solution to extract spatial features. And among them, this is the way, okay? This is one for example. One of the most powerful structure element style, it is the morphological profile. We can say even now with the huge development of deep learning based approaches, I think extended more morphological attribute profile or morphological profile still can have one of the best results in the literature, and it has a very good generalization, because if we implement morphological MP or EMIPs to any of the remote sensing data, and we can have very reliable result. Deep learning, not aware always, because it depends on the training, okay? So this is a very simple style. We have Hyperspectral data, we perform feature extraction by PCA. We use PCA, of course. We don't need to do PCA, but we do PCA. We can reduce the dimensionality. We can have independent principal components, and we can remove noise. It has a lot of advantage. And the important thing is with these principal components, it is more than enough when we do morphological profile. There's no very much big difference on the performance that we do morphological profile on the original data or on the principal component analysis dimensionality reduce the data. And then, but the computation time or cost is much reduced. Then we have a lot of morphological profiles. Then we have the extended morphological profiles. Then we do a classification, simple classification on the morphological profiles, and we can have a very beautiful result, as we just mentioned. Okay. Then the other one is random field. Random field is one of the is a Bayesian approach. Is a Bayesian approach. Here we have the data model. Here we have the data model here, right? And we have the data model here. We have the spatial information here introduced here. Of course, we have a normalization term here. If it is just a normalization term, or we don't consider it is, this is a microphone on the field, and it's up to how much we consider it. It is this DIF discriminant random field or conditional random field. Anyway, this is to introduce the global dependency system. It's through this term, okay? Through this term, we can introduce the global dependency system. Anyway, here we can see, here we have the first term, we have the data term. We introduce the density function of the class density function here. We have the data term. And here we introduce the spatial information through the clicks. It is about the neighborhood, right? So that means the samples, if they are in the neighborhood system, they are more likely to they're having the same labels, and if the probability that they have the same label are much higher than if they have the different label. This is a random field. It is also studied a lot in the literature, and in the spatial representation based classification. In the spatial representation based classification, there are two ways to introduce the spatial information. One way it is to introduce a weight, a spatial weight. Okay, here for example, we can have a spatial weight here, we can have a spatial weight here. To throw a weighted system. The weight system, of course, this is a weight, neighborhood weight. There are two factors, is the neighborhood weight and the neighborhood importance. In this neighborhood system, in this neighborhood weight, we have of course the number of the neighborhood pixels, and it has advantage, and of course the very important advantage is that the complexity of the solution of this, the optimization of these objective functions, they are more or less the same, not a huge difference. And we can introduce the spatial dependency system simply through this weight. This is the first way. Another way it is through a spatial recognizer. For example, we can have the touch variation. Touch variation here to introduce the spatial recognizer, and also we can, for example, some of the work use the non-local touch variation here to introduce the spatial information as a spatial recognizer. Of course, there's some of the work to use both through the weight system, through a weight function or weight matrix here, and through the regularization system. Here we can, when we introduce a regularizer, the optimization is much more difficult, but around we have good solutions, solvers to optimize this very information. And another one is a segmentation based approach. This is a very lot used approach. For example, we can use some approach and edge function, or we can use, for example, segment hierarchical segment style. This kind of approach to have a segment. Then we use this segment to have this. Each segment, then we can perform this segment-based approaches to perform this segment, okay? In this way, the information of the neighborhood system, the neighborhood are introduced in this segment, and the weight also can be defined inside the segment. This is in this way, we can see that it is adaptive. It's an adaptive dependency system. And another style is a deep learning approach. From here, we can see that, for example, this is a tutorial in 2016 in Hpc Geoscience and the Remote Sensing magazine. From here, we can see the deep learning approaches. They're not only used in hyperspectral image, of course, they're also in higher spatial resolution image or other data, higher resolution data, or image database to perform deep learning. And the main difference between deep learning and the other feature extraction approaches, it has a back propagation. Of course, it has a back propagation step to introduce the class information to tune the features, obtained features, or to optimize the obtained features. And that means to somehow to secure the obtained features are good. Okay, if we simply perform the feature extraction, sometimes the features we obtained might not be good for our problem. But in this case, when we do deep learning based, use the back propagation, that the features are optimized by using the labeled samples. And here I'm going to introduce a work, and now it is already published, okay, in March in 2020, and it's is a work published by my group. We call it is naive gap networks. Why we use gap networks? Okay, why we introduce these gap networks? Because we know gap networks has very strong. They are very strong when we do normal feature extraction, right? We can have very powerful result. So if we can integrate the advantages of gap filtering and the neural networks and use this back propagation style to tune the gap filters, we are thinking that we should be able to, or we are expected to obtain better features. And compare with CN, it has much less, normal CN, it has much less parameters, right? So it is a predefined feature, of course. I think my connection is, okay, now my connection should be okay. It has a predefined kernel. So it is expected to have a fast optimization or fast convergence. And it has limited number of parameters. Compared with CN, it has much less parameters, okay? This is also available. The code is also available in GitHub, okay? So we can see here, what I want to show to discuss here, it is, we can see here, if we use normal CN, we can have a lot of features. Of course, we have a lot of features, as we can say. CN use random kernel. So the features we obtain of course, has some characteristics of randomization. Some of them are quite blurry and they're random features, right? But if we use gap filters, gap nets, gap kernel, we can see the features with good orientation and with good orientation and structures. Okay, for the first patch and for the second patch, we can see the same. For example, these features are random, has some randomization, random properties, but these features, what we obtain, are very specific. Okay, so now we are going to show some result. This is some classification result. From here, we are just going to show the property of different pre-processing, the feature extraction approaches are integrated or post-processing. From here, we can see for the raw data, of course, we have some paper and short noise, right? We can see here. This data is a difficult data because the longitudes are very limited. So we don't show the accuracy as we think there is no point, or it is not so important to show the accuracy. We just to see the effect. From here, we can see a lot of paper and short noise because it is a pixel-wise classification. For the pre-processing, we can have some homogeneity, but we still have this paper and short effect. This is because it is a feature-wise classification. In the features, in the obtained features, when we perform classification, we still assume that each pixel they're independent. Okay, so it still has this paper and short paper sort effect. Okay, when we see the integrated and the post-processing, and then we can see in the post-processing, we have much more effect of the over smoothness. It is easy to can see here these areas that it is over smoothness, over smooth. Okay, in the integrated, in the end we can see somehow in this image that they are better preserved. First, it can preserve the homogeneity. Second, it can preserve the textures. Okay, and now we're going to see some of the result of the gap analysis. When we use gap analysis, as we say, it's predefined kernel. It has a predefined kernel. It has much smaller parameters. Since it has much smaller parameters, so it can tackle the problem which has parameters. Okay, it has a much smaller number. When we have a smaller number of training samples, we can get a better classification result. And actually, it's quite a good classification result compared with, for example, these other approaches of SCN or CNPPF. These approaches, they cannot even, very difficult to run in this condition, okay? And the most important thing is that the effectiveness with the small number of training samples. Okay, finally, I'm going to give some conclusion. In the conclusion, we introduce a spatial dependent system through label pixel dependency or label dependency. We can introduce the spatial correlation, and in such a way, therefore, to introduce the spatial correlations into our classification. And also we introduce we think that the deep learning plus a priori information, we call it is, for example, predefined kernel. We use a gap kernel, and we take advantage of both the predefined kernel and the deep learning can have very beautiful or impressive classification performance for our problem, because we know our problem, we know what it is for the Hyperspectral Classification, we know what is the problem we have. For example, we have limited training sample, and we know it has a lot of structures. It is like more clear to have structure information, spatial information, and it works very well with the gap kernel or wavelet kernel. So we can use a predefined kernel to plus the deep learning strategy to define some new approaches. Okay, thank you very much. This is my talk. Thank you again for the invitation, and I'm very happy to give this presentation. Thank you again.
Thank you, Professor Junli. Can you hear me now? Professor Junli, can you hear me now?
Yeah, I can hear you. I can, yes.
Okay, thank you. Thank you for this very useful talk, which will be very informative for those researchers who are working in the field of subpixel mapping and super resolution mapping, I'm sure. You have very elaborately stressed upon the spatial and spectral classification of hyperspectral data, and how important it is to jointly consider spectral and spatial data for classification. And you have also discussed about the spatial dependency systems, considering adaptive dependency, fixed dependency, global dependency. And you have also discussed about the paradigms of spectral spatial classification, where one can use pre-processing based classification, integrated classification. You have also stressed upon the use and importance of deep learning in hyperspectral image classification. And lastly, you have elaborated on the use of naive Gabor networks for classification of hyperspectral data. Thank you very much, Professor Jun Lee. Again, I would like to give an introduction after your talk, as there was some problem in connectivity. I would just like to give a brief introduction for our participants. Professor Jun Lee is presently a professor in the School of Geography and Planning, Sun Yat-sen University, China. She received the MSc degree in remote sensing and photogrammetry from Peking University in 2007 and the PhD degree in electrical and computer engineering from Instituto Superior Technical University of Lisbon in 2011. From 2011 to 13, she was a postdoctoral researcher with the Department of Technology of Computers and Communications, University of Extremadura, Spain. She has authored or co-authored more than 160 publications, including 113 journal citation report papers, more than 80 in IEEE journals. Her citation record, according to Google Scholar, is 5262 citations. H index is 34 and I-10 index is 77. Her main research interests comprise remotely sensed hyperspectral image analysis, signal processing, supervised and semi-supervised learning, fusion, and active learning. I would also like to mention that Professor Lee received the prestigious IEEE Geoscience and Remote Sensing Society Early Career Award in 2017 in recognition of her outstanding contributions in innovative hyperspectral and SAR image processing algorithms for remote sensing. She is currently serving as an editor in IEEE Transactions on Geoscience and Remote Sensing since 2019. She is presently the editor for the IEEE Journal of Selected Topics in Earth Observations and Remote Sensing. She was from 2014 to 18. She coordinates several projects funded by the Chinese National Science Foundation, the Ministry of Science and Innovation of China. The total amount of funding obtained with these projects is more than 1 million. So she is a senior member of IEEE since 2014, and she has recently been elected as a voting member of the Administrative Committee of the IEEE Geoscience and Remote Sensing Society for the period 2020 to 2022. So, Professor Jun Lee, thank you very much for this informative session. And
thank you very much.
Thank you. Please be with us. We have several questions. We also have Professor Antonio Plaza with us. So I would request all our panelists to please like switch on their video.
If I switch on my video, I will lost the connection again. I should not switch on my video.
Okay, fine. So can we start the questions, question answer session? There are several questions from the audience. I will just read them one by one. The questions are for Professor Durga as well as Professor Jun Lee. The first question, I think, is for Professor Durga. How can we prepare against disasters and natural calamities more precisely to save human life through prediction and real-time information of remote sensing and GIS?
Sorry, I didn't hear very well. Maybe you can write in the question box, then I can see better because I cannot hear you well.
Yes, this question is for Professor Durga. can you please unmute
Oh,
yourself?
not for me, right? Not for me. Okay.
The questions are in the question answer box also. You can read them. Can someone, the host, can you please unmute Professor Durva?
Sir, please unmute your. Sir, please
Yes.
unmute your
Yes.
mic.
Yes,
Yeah.
yes.
Yes, sir.
See, I've already answered all the questions there in the Q&A. Can you please check? I just typed the answers. I just typed the answers to save us time, so anybody can just read them.
Okay, okay. So you have answered live.
Yeah, I answered them already.
All of them. How do we overcome the problem of poor spectral resolution in Landsat data? I think this question is for Professor Jun Lee. How do we overcome the problem of poor spectral resolution in Landsat data?
Okay. Okay. I don't see the question here, but the poor resolution of the Landsat data, right? The spectral resolution. The data is the data. The data is the data. What we can do is we can try to exploit the data. No other way. For example, the spectral resolution is not so high. We can try to use the spatial information. Okay, we can try to exploit the spatial information. And what it can with the spectral resolution, for example, for Landsat data, what kind of problem or what kind of application it can be done or it cannot be done. It is defined by the data. Okay, the data is the data. So the first point. The second point, if we want to better exploit, of course, is we need to use the spatial information. We can do feature.
Yes. I think we have lost the audio. Professor Jun Lee, can you hear us? I don't think she's.
Internet connectivity issue.
I think she has. Professor Plaza, can you answer on behalf of?
Yes, can you please repeat the question?
The question is, how do we overcome the problem of poor spectral resolution in Landsat data?
The limited spectral resolution, right?
Yes.
Yeah, one of the possibilities to try this kind of punch sharpening, or you know, because maybe we have hyperspectral data with different or similar spectral resolution, and then you have the Landsat data. So there are some punch sharpening techniques which basically try to fuse the properties of both sources of data. So maybe the Landsat data has relatively good spatial resolution, 30 meter. Then you can also use some other core registered hyperspectral data and try to fuse the data. Of course, you need powerful registration, and it's not always easy to manage this kind of multimodal fusion problem. But there are some techniques, and actually there was a question about this in the forum, and I already recommend some papers talking about multimodal fusion of remote sensing data. So if you go to the forum, I already replied one question on this, and I put a list of reference there that you may check.
There is another question. Does modeling topological relations like decision tree contain tree prune logic? I think this is for Professor Durga.
why I'm not answering here is a little bit more references to papers I've put there on the there, so that they'll get more elaborate information. Yeah, they may please check on the Q&A box.
How do the EMAPS technique work typically on the ground level of analysis?
This is for Professor Jun Lee, maybe?
I think so. How do the EMAPS technique work typically on the ground level of analysis?
On the ground level. I'm not sure what it means, the ground level. The EMAP is basically extended morphological attribute profile. So basically, the idea is to apply a series of opening and closing, where the opening is erosion followed by dilation, and the closing is the opposite, dilation followed by erosion. So the idea is to hide the spatial information in the neighborhood. So I guess the question is at the ground level, maybe the ground level, he or she is talking about the raw data. Anyway, it's a very powerful way to obtain information in the spatial domain. You can get information about the object, about the surrounding.
So one question is, what is the mixed pixel solution at boundary? How to overcome mapping of mixed pixels at boundaries? I think this is a question of subpixel mapping.
Yeah, subpixel mapping is
Yes.
is a problem, especially at the boundaries. This really depends on the spatial resolution of the data. If you have high spatial resolution in an image, then somehow you can assume that the borders are pure. But for example, with Landsat data, sometimes 30-meter or even more coarse spatial resolution is difficult to give a classification, because you are basically assuming that everything inside the pixel is pure, and in 30-meter maybe you have a lot of mixtures. So in this case, I recommend having a look at the lecture I gave last week about the mixing, because I described some techniques for being able to deal with this problem. So if you feel that in the border there are some mixing problem, you could use a mix in the borders or even in the whole image. And there is a lot of there are a lot of techniques for mixing. So maybe the person asking the question can take a look at the video of the seminar last week, because we talk a lot about mixing.
Yes. This another question for Professor Jun Lee. Is it possible to generate a super resolution spectra from lower resolution spectra?
That's a good point also. There have been some techniques using deep learning, for example, generative adversarial networks, GANs, and there are some efforts trying to generate higher spectral resolution data. There's another way is to use spectral libraries, because now we have a very detailed set of spectral libraries from almost any kind of material that you can find on Earth. I'm talking about minerals, vegetation, water, and so on. So there are some interesting works. They use, for example, some Landsat data or lower spectral resolution data, and they try to interpolate the spectra using as a reference some library, some spectral library, and some prior knowledge of the data. So These would be the two ways, the two kind of approaches I have seen in the literature to generate higher spectral resolution. Another way you can go is try to fuse data from multiple sources. Like, for instance, if you have, let's say you have a Landsat data and hyperspectral data from the same location, from the same area. You can try to fuse those data. And in this case, you get the advantage of the spatial resolution from one data set, resolution from the other data set. But again, you need some powerful registration.
Yes, but what if there is a time gap between the two? If they do not belong to the same time period, it may happen because it is very difficult to get time series hyperspectral data.
Yeah, that's exactly the point of deep learning, using deep learning to use generative adversarial network in case you don't have any reliability on the data. Because, for example, for vegetation, you are totally correct. It might be that the spectral library was collected in a different season, and now we are taking the image in a dry season, and maybe we have the library from the humid season. So in this case, the spectral match will be very difficult. It's a difficult problem, and that's why it's not straightforward to increase the spectral resolution. But there are some papers, so maybe I can post later in the chat, in the discussion forum. I can post the papers I know about GANs and also about the spectral library.
Is there any specific interpolation method image fusion, or maybe filling up the gaps of multispectral data with hyperspectral data? So the question is there any specific interpolation method that you would suggest?
Yeah, it's similar to the previous question, how to match the multispectral and the hyperspectral. The thing is, I believe the mathematical interpolation methods are difficult, because in this case, in order to properly reconstruct the spectrum, we need some physical knowledge about the material, because mathematically you can try, but you also need the physical information. So that's why I would prefer to use a library, because I can see a real example of what a spectral signature looks, the one we want to obtain, rather than a mathematical method or mathematical interpolation, because it can lead to a kind of fake spectral signature, and then it might not be realistic. So I think it's better to use some kind of reference spectra. In this case, I would suggest using spectral library for the reconstruction.
Yes. Thank you. I think this question is for Professor Durga. With small training data, will deep learning be useful?
I think you need to unmute Professor Durga.
Kindly unmute yourself.
Yeah,
Yes.
I think this is an issue that a lot of people are struggling with when working with small training samples for deep learning. I think small training data is not very favorable to do deep learning. You need a large number of training samples. But of course, some of these earlier speaker has talked about Gabor nets, those kinds of things. Seems to be smaller. They did some work related with small sample sizes. So probably some innovation in deep learning with small sample sizes is probably in offering.
These are some of the questions that we. Another question is, can it be merged with normal satellite maps to know the exact locations of highly affected areas and make differences of low, medium, and high affected areas?
Yes, of course. Yes, of course. Yeah.
Yes.
So, whatever analysis that you carry out on a satellite image, basically it carries with it the location information, the latitude, longitude. You can definitely transfer it on normal maps. You can, grade it, make it in different grades, low, medium, high, all those kinds of things. And then you can transmit those maps to anybody. Sure.
Yes. Another very important question, I think, how can we comparable different sensor data like Landsat and Hyperion in the same scale? They want to bring it in the same scale. Or Professor Junli?
Sorry, I didn't get the question. You're talking about bringing?
I think what the participant wants to ask is how to bring Landsat data and Hyperion data in the same scale. Maybe they want to use it for fusion or classification. So maybe they need to bring both data in the same scale. So how to make it, how to bring it to the same scale? I think this is the question.
Yeah, I think in this case, if I'm not confused, I think we have the same spatial resolution because Landsat and Hyperion, they both have 30 meter in terms of spatial. So in order to bring to the same scale, you need to manage the temporal dimension so that the data are collected more or less at the same time. And also you need the registration. You need to have a powerful registration algorithm to make the data sets match. But Landsat and Hyperion would be a very good candidate for matching because you start with the same spatial resolution.
Very true. I think we have answered most of the questions that have been raised. Can I request Honorable Vice Chancellor Sir to please join us once again? I think Professor Junli has got disconnected now. She is not
Yes,
here.
yes, she lost her connection, but we are thankful to Professor Antonio. He has volunteered in clearing this, clarifying the queries and clearing the doubts of many of the participants. Thank you, Professor Plaja, once again.
Thank you so much. Thank you so much, Professor.
Thank you very much. So would you like to say anything about this session, Professor Plaza? You have been with us in the last session as well, and you had discussed about spectral unmixing. And so how was this session? Can you hear us? Can you hear me, Professor Plaza?
Participate in this seminar series is a very nice initiative, and we are all learning a lot and having the chance to interact. So I'm very happy to participate in this seminar, and I will continue attending the seminars as far as there are new sessions organized. So thank you again for having me.
Thank you.
Hello, Professor.
That because of participation, there is an overwhelming response amongst our participants, and we would like to have again with us for enriching our knowledge, to encourage our participants.
Surely. And Professor Durga,
My pleasure.
you were saying something?
No, it's a very good series of talks that you have. But I missed yesterday. But yeah, the other talk given by Professor Lee was very interesting. I'm sure a lot of information I could gain from it. Thanks a lot.
Yes. And, sir, would you like to say something about the session?
I would like to extend my heartiest thanks to Professor Dhruva also because of his nice and elaborate presentation. Unfortunately, Professor Lee got disconnected, but she also presented with the full of energy. I was listening both of these lectures, and it's really, though I do not belong to this subject, I also learned at least a little bit of things from my participants about the lectures and for deliberation of Professor Plaja, Professor Gopalan, then Professor Dhruva today, Professor Lee today. And thank you. We would like to have you again and again with us.
Sure.
So with this, I think we can conclude today's session. We have a question. We have an online quiz for the participants, after which they will get their certificates maybe after 2-3 hours, and conclude today's session. On behalf of the university, I would like to express, in fact, we would like to express our sincerest, heartfelt gratitude to all those whose active participation and support has made this endeavor a success. So firstly, I would like to express our sincerest thanks to our Honorable Vice Chancellor, sir, who has always mentored and tutored us to the righteous path for hosting such an event. We are all delighted to have with us Professor Junli, Professor Durga, and Professor Plaza, who have really enlightened us with their expert views.
To encourage all the participants to join again at our forthcoming webinars in this area, in this subject.
Right. So I would also like to mention that next Saturday we have the third and last webinar of the series. So I would also request all the participants and our experts today as well to join next Saturday, that is the 13th of June. So with this, I would like to thank all of you for joining the session, and thank you all. And I would request the participants to please complete the quiz that is given to you. A quiz link has been given to you. Kindly give your answer and you will get your certificates. Thank you all very much.
The participants are advised, encouraged to use the
Pardon, sir,
so we created a discussion forum.
Yes, I told them that we already have a discussion forum, and whatever questions you have in your mind, you can answer. You can post your queries to the discussion forum. The link has already been provided in the chat box. It is MAKAUT blog.geo.blogspot.com. So you, all of you can post your queries, and I request all the experts to please respond to them. Okay, sir.
Okay.
So
thank you very much.
Thank you. Thank you all for joining.
Thank you. Bye-bye.
Thank you very much.
Okay, so please, I request the host to please display the link once again. Link of certificates and quiz. The participants are requested to take a screenshot so that they can access the link later on.
Ma'am, shall we close the session? Ma'am, shall we close the session? Hello? Hello? Hello, Manas sir?
Hello.
Yes.
Ma'am, we shall close the session?
Have they answered the quiz?
Yes, ma'am, we are getting the responses. Once again, I am sharing the link now.